Today's lesson, section 2.7a, we'll be talking about one-to-one functions and their inverses, okay? So a one-to-one function is a function where each value in the domain goes to, or you could say that it maps to, only one value in the range and vice versa. Now what this means is, if you have a function, remember we said a function is where you have 1x going to 1y, okay? So 1x can go to two different y values that had to go 1. Now, one-to-one function is that same concept, but also has to do the same thing backwards. So the y value only goes to one x value as well. So you can't, like a y value, one y value can't go to two x values. So like, let's look at these two examples down here. So our function for g, you can see that 4 goes to 10, 3 goes to 2, 2 goes to 3, and 1 goes to 2. So each x value goes to one y value, and that's fine. Okay, so it is a function. But if you look backwards, so 10 goes to 4, 3 goes to 2, but 2 goes to 3 and 1. So because 2 goes to two different values, then this function is not a one-to-one function. Okay? But let's look at the other one. So for function f, 4 goes to 10, 3 goes to 4, 2 goes to negative 3, and 1 goes to 6. But if you look backwards, 10 goes to 4, negative 3 goes to 2, 4 goes to 3, and 6 goes to 1. So each of those y values goes to one, exactly one x value. So f is one-to-one in this case. Okay, so that would be an example of what not one-to-one and what is one-to-one. Okay? Now another way of taking notice of this is using the horizontal line test. Now kind of like how we use the vertical line test to determine if a relation is a function, we can use the horizontal line test to determine if a function is a one-to-one function. So we can say a function is one-to-one if and only if, and that's what this IFF means. If and only if no horizontal line intersects its graph more than once. Okay? So same concept as a vertical line test, you're just using horizontal lines instead. So for x to the fourth, if I want to see if the following functions are one-to-one, I need to graph them to kind of take a look. So let's pick some x values. So if I do 0, 0, 1 is, or 1 to the fourth is 1, right? Negative 1 to the fourth is 1. And 2 and negative 2 to the fourth are 16. So you know that they're going to be high up there, so we don't need to go crazy with our graph. We just need a general sketch to help us prove this. Now looking at horizontal lines, if I draw a horizontal line, oh, there I crossed my graph twice. So this function is not one-to-one. Okay? Now let's look at x cubed. So here, if I do 0, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. So right there. And then the same the other way, we've graphed this many times in our other problems. Okay, so you get a graph that looks like this. Okay, so now here, if we look at x cubed, I can draw many horizontal lines. Here I don't cross my graph ever twice, so this one is one-to-one. Okay, so that's kind of what they're looking for if you're using the horizontal line test. Okay, now let's look at the inverse of a function. Okay, so let's say we let f be a one-to-one function with a domain A, looks like I was missing that, domain A and range B, then its inverse function f of negative 1, okay, so f to the negative first power is how it's written, has a domain of B and a range of A. So notice how the domains and ranges switched when it became an inverse function. So it's defined by f inverse y is equal to x, which is this, like when you switch it back, f of x is equal to y. Okay? So notice how the y and the x switch spots for one function to another one. And this holds true for any y in the set B. Okay? So what that's trying to tell you is that if you have a graph of f of x equals y, then switching the x and y values is how you define the inverse. But this only works if your function is 1 to 1. Your function does not have an inverse if it's just a regular function. Okay? And it's not a 1 to 1 function. Example 2 wants us to state if f of 3 is equal to 4, f of negative 1 is equal to 6, and f of 2 is equal to negative 10. Then they want you to find f inverse of 4, f inverse of 6, and f of inverse of negative 10. Okay? So using this concept that they described earlier, because of those switches, you can do it the other way. So because this is your x and this is your y here, if you're now looking at f inverse of 4, okay, remember those values switched up there. So this is your y value, 4, so my x value that's related to it is 3 because it's a 1 to 1 function. Okay? F inverse of 6 looks like it'll be my x value, which was negative 1, and f inverse of negative 10 is going to be the x value for that, which is 2. Okay? So the inverse of any y value will be its corresponding x value, because they only have one attached to each other. They're always intertwined that way. Okay? Now, one property of inverse functions that we can use to help prove if two functions are inverses of each other is let f be 1 to 1 with a domain A and a range B. The inverse function of f inverse would satisfy the following cancellation properties. Okay? So if we use composition, so f inverse of f of x, we should get a value of x. And this x is true for any x in A. And then we can also do the function, or f of f inverse of x, which also gives us x for every x in B. Okay? So to prove if a function or functions are inverses of each other, we would need to use this property of compositions both ways and get the values of x and x in the end to show that they are functions, is basically what they're trying to tell you. So, for example 3, it says show that f of x equals x to the 4th and g of x equals x to the 1/4 power are inverses of each other. Okay, so we want to show those two functions are inverses, so we need to do f of g and we need to do g of f. Okay, so remember that's f of g of x, and this is g of f of x. So if we can get them both to equal x, then we've proven our point. If one of them does not equal x, then they're not inverses. Okay? So g of x is x to the 1/4. So let's plug that in. Remember that's to the 4th power. Power property, or power to power property. Here for our exponents, 1/4 and 4th. Remember that's from chapter 1 that we kind of reviewed. So multiplication between the two, so 1/4 times 1/4 gives me x. So that's what I want. So that's a check. F of x is x to the 4th. So then plug that into the function of x to the 1/4 power. Same thing. Power to power property tells me to multiply. So 4 times 1/4 gets me 1. So I'm left with x. So in this case, these are inverses. So that's kind of what you're proving for that example. Okay, and then the last thing is graphing the inverse of a function, the graph of the f inverse is obtained by reflecting the graph of f in the line of y equals x, or over the line. So here if I have a graph, okay, and let's say they want you to graph f of x square root of x minus 1. So remember, square root of x would be 0, 0, 1, 1, and 4, 2. Okay, so remember on the inside you're always moving the opposite direction, so since it's minus, you're moving it to the right. So it'd be 1, 0. I can write these values down for you. So 1 gets us 0, 2 gets us 1, and 5 gets us the 2. Okay, so that would be my graph of f of x. Okay, let's go with a different color. So f inverse of x is going to be reflected over the y equals x line. Okay, so that means x and y are switched like we did in our example 2 that we talked about. Okay, so since I have these values written down, so instead of your x being 1 for the first one, your x is 0, and the y value is 1. And then 1, 2 would be a point, so it's like you're taking these points and switching them, or switching their spots. So I get 2, 5. So then now your graph looks like this for the inverse. Okay, so that would be f inverse of x. And that's how you would sketch the graph of an inverse using the original. Okay, have fun.